Okay, welcome everybody to our webinar on the FourierBMS equipment. My name is Mark Errington and I'm a director of the company with 25 years of service inside the business. As Pavlos said, there will be an opportunity to ask questions at the very end, and if we use the emoji thumbs up, and we'll go through your questions one by one. But first, I thought I'd give you a little bit of history about our belt tensioning and belt measurement systems. We were first introduced in the late 1980s a handheld belt frequency meter, which we actually had a patent for measuring the belt vibrations through acoustic means. We are still producing this meter now, albeit we have now got the ability to use optical sensors as well with this, and it is endorsed and produced on behalf of Continental and SKF. So it's known in the market as being the best handheld service measurement device there is. So after this, it's naturally led us into the mass production manufacturing side of belt measurement. And during the 90s, we produced equipment that was used by Ford and Ducati to measure their auxiliary belts on their engines, and we're still producing equipment for Ducati for their production lines. So the natural progression beyond that was we were requested in 2007 to produce a piece of equipment that could measure the belts on electric power system steering units, or EPAS for short. And we first did this in 2007. So the FourierBMS is born from this very, very first control system that we had. As you can appreciate, as time goes by, we learn more. We get our clients' requirements. They all have different elements and what they want for their production lines, and the FourierBMS is born from that. So that was just a brief history of the company and how we've been involved over the years with belt measurement and belt tension. And Pavlos now will talk you through the FourierBMS cabinet and its functionalities and its abilities to analyze belts and the signals coming from them. Over to you, Pav.
All right. Thanks for the introduction, Mark. Hello, everyone. My name is Pavlos Sgardelis. I'm a lead engineer in the R&D department of Clavis, and I'm a senior engineer here in Clavis. This webinar, as you know, is for the FourierBMS. It's for belt tensioning measurements and systems and controls. Before we start, I would like to say that this webinar is being recorded. Now, I'll start by saying what is FourierBMS, and then we're going to go into depth into a bit of more detail of how the FourierBMS works, what kind of outputs it gives, and why is it important. And also, Mark is then going to speak about some more processes at the end. And then eventually at the end, we'll have a questions and answers session. Now, to start with, why is tensioning your belt important? So, in a belt pulley system, we have two pulleys and one belt. There are two key parameters that need to be checked. The first one is the pulley alignment, and the second one is the belt tension. And that's where FourierBMS fits in, and that's what the FourierBMS does. It controls the tension or gets readings from the tension from the belt. Now, if this belt appears to be faulty or if it fails, actually, in the worst case scenario, it can lead to engine failures. In order to do so and to avoid costly downtime, we need a better process of finding out what the tension of the belts is. And here enters the FourierBMS. We can actually measure the frequency of the belt, the natural frequency, the eigenfrequency of the belt on which it vibrates at, and thus determine the tension that it is in. Because these two quantities are directly linearly related. So as the frequency increases, the tension increases as well. And actually, as the tension increases, the frequency increases. So we can take measurements of frequency in hertz. Our cabinets, our systems can measure typically from 30 hertz to 500 Hertz, but this is not the full range. We can do more than that. We can go up to 800 Hertz, for example. The measurements are given in Hertz, so we are measuring frequency, but we have the ability also to give the actual tension of the belt, either in newtons, pounds, or kilogram force. But in order to do that, we need to have the mass of the belt. We need to know the mass of the belt and the span, or the length of the belt from pulley center to pulley center. Why to use it and where is this used? The BMS is, we have divided the applications into three main categories. The first one is the electric power assisted steering systems, or EPAS in short. The second one is the auxiliary belts in the production line of the vehicles. And the third one is a combination of any possible system that has a pulley belt configuration, where we can measure that the tension needs to be measured. And one of these examples is the transport refrigerator units in the big lorries. A little bit about the design. This is the sensor head, which actually reads all the data. Here we can see that we have a hammer which agitates the belt. That's its purpose. And then we have an optical sensor here that takes all the vibrations in terms of analog readings and passes them to the cabinet. Then this signal is getting digitized. A lot of magic happens within the cabinet, and we get out the frequency that the belt vibrates. Now we have two main models. The first one is the BMS-03, which is the read-only module, where the operator can see what frequency the belt vibrates at and if it is according to specifications. So the part where the specifications are set is on the control section, where we can have RS-232 communication from the plant or Ethernet communication from the plant. And then on top of that, we have the most simple way of communicating, which is the auxiliary I/O port. Usually we'll see that most of the customers use the RS-232 port for communication. On top of that, we have extra outputs to visualize better and look in depth the signals coming out from the sensor heads directly before the digitization. And these are the three BNC cables that can be connected to any oscilloscope. Now, this is the port for the sensor head, as we said. And in the front panel, which is the interaction with the operator, we have the slack-OK tight. That means that we can have that the system knows whether the belt is set to the correct tension by providing an OK signal. And if it is slack, we have this indication here. If it is tight, we are over that, so we have the other indication. And we have a series of buttons here. The one is to switch the LCD from the time domain to the frequency domain. We're going to talk about the frequency domain later on, which is an important aspect of the whole process. We have a save button to save the image that we have here into a USB port that we can see here, or hold the image for further analysis. And then we have the run button, the calibration for calibrating this system, and the run into fast Fourier transform or frequency domain. The frequency is indicated here, and then we have the quality factor, which also is an important aspect of this process. We're going to talk about this later. Now, the second model is more advanced than the first one. We not only have the same abilities that the FourierBMS 03, which is the previous model, has, but on top of that, we have two main extra features. One of them is that we can display the actual tension of the belt, but the plant needs to provide as we said, the weight of the belt and the length of the belt in order to do so. So we can actually output this. And the second most important feature that this cabinet has is the ability to control a power tool. Now, By controlling the power tool, we can actually control the tension of the belt. So we can readjust the belt in real time based on the readings that we get from the sensor head. So that means that we can have a start to finish process within one station of measuring the belt and readjusting it. And that's called the closed loop. So we are getting readings, we are adjusting the belt, and we're getting readings up until we have the OK signal here. This is done via a PLC inside the cabinet. So we are utilizing a PLC, and because we have a PLC, we have extra communication protocols available, which is the Profinet and Profibus with the plant. On top here, we can see that we have also an extra output for a light stack. Usually you will find out in the environment of the production line that the cabinet is well hidden behind a massive panel, let's say, so the operator cannot see the indications. So that's why we have a light stack, which we're gonna see later on in the video, that can provide feedback to the operator of how the process goes, if the process has finished or any other indication that the plant wants to give. Now, because we have the PLC on the BMS 01, we have the ability to store data. And this can be either the tension, the actual tension, or the frequency in hertz, any events, any configurations, and any logs that are coming to or going out from the cabinet can be stored in the PLC. Now, all this is good and easy in an ideal world. But in the real world environment, we have, this is far but true. So the belts do not vibrate in a single frequency. We have multiple frequencies lying in the belt vibration. So that means that the belt can vibrate into multiple frequencies across the 30 to 500 hertz gap. And this is because we have different designs, we have different belts, we have teethed belts or non-teethed belts, and we have the ratio of length to over width, which actually complicates things. Because we have two main frequencies at least. One is the length frequency, which we are interested at, which describes the tension, and the other one is the width frequency. And if these are too close, then we can have a problem. This means that multiple frequencies in the signal means like we have a complex waveform coming from the output of the cabinet. And the question is, how do we determine which one is the dominant frequency, and how do we determine which ones we are interested at? And the answer is, the solution is that we go into the frequency domain. Now, the frequency domain is actually a step further from the time domain. Here we can see the time domain, we can see the vibrations in real time, how the belt vibrates on one point in real time, but that's fine. We don't see though what kind of frequencies with naked eye exist within the signal. So that's why we go into the frequency domain in order to get a better representation of how many frequencies and what their power is. When we say the power, we actually want to determine which one is the dominant frequency over the rest of them. So as an example here, we can see that this belt vibrates in 117 hertz. We can see a very profound peak here, which is our dominant frequency. And then we have a smaller frequency. Well, we have a peak here around 450 or 450 hertz, which might be the width vibration. So because we know that the dominant frequency is always the length module, we go with the dominant one. But that's the way of dividing each of the peaks in the sine wave. But the question now is, how does the system know which one to pick? And the answer comes from the quality factor, which is a method, a devised by us method, in order to clarify whether the signal coming out from the belt is good in terms of quality or not. So if the signal is pure, that means that we have one sinusoidal going from some of the beginning to end. That means that we have a good quality factor. So we give it a 10. The quality factor can take values from 0 to 10. So we can give, if we have multiple frequencies and if we have low amplitude in our signal, or if we have, or if we don't know which frequency is the dominant frequency, the cabinet, the system will provide us with a low quality factor. That means that we cannot trust the data. And this usually is because of the incorrect positioning of the sensor head as in relation to the belt. Now, speaking about the sensor head, this is how the sensor head looks like. We've talked about the cabinet, which is the bulky main unit. This is the sensor head where actually its purpose is to agitate the belt and take readings only. And we don't have any more complex electronics in there because we need to have different designs. And by having a minimum electronics in the sensor head, it allows us to have different designs that we can see here. This one is the compact one, which is the most popular product that we have. It's being used on belts that we can have easy access at. For processes that require the operator to hold the sensor head, we have this one, which is a handheld sensor head. If we have multiple belts into the production line with different widths or spans, then we can have the adjustable head here, depending on what the process is, of course. And then finally, we can have the long reach head for belts that they are that can be not easily accessed with a bulky, with this actually standard head. Going into detail of the two most popular ones, the compact sensor and the long reach. In terms of the compact sensor, it's pretty straightforward. We have an optical sensor here and a hammer. The hammer agitates, the LEDs take the signal and pass it to the cabinet. Now, I would like to stress out here that all of these sensors have the ability to be connected to one of the two units that we've described above. And then for more complex designs, Mark is going to speak about what we can do in order to overcome any problems that you have with the design, or if the belt is not easily accessed. Over to you, Mark.
Thank you, Pavlos. Yeah, okay, so as Pavlos has previously mentioned, we've got this, what we call this long reach sensor head. And actually it was born from a request from one of our clients where the access to the belt was through a small hole. And so the standard shape of head would not meet the requirements for that. So we've got this 18 mm diameter nose that would fit through the hole. It's got a little piston pin that would fire against the belt, and it would detect the belt vibrations in exactly the same manner as the compact sensor head. So the image you can see on there is actually a requirement from one of our clients in a generator unit, where he wants to agitate that belt, as you can see on the screen, but also have what we call a mounting fixture that allows it to be securely located onto the unit and do its job of looking at the belt signal. So because we've got a fully capable machine shop on our premises, it gives us the flexibility to not only produce the heads and the shapes and sizes of the sensor heads that are required. It allows us to make the fixtures and do some proper investigation work with the units that we're being asked to measure. So our catalog is quite extensive. We've got 61 available shapes and dimensions of heads already in the catalog, but of course we can adapt the concept and produce any shape and size that to meet our clients' needs. And we're working on reducing the optical sensors even further to give us a more scope to measuring even smaller belts with sort of widths of 4 mm. So that's really where the long reach came from. It came, as I said, through the need to look at belts through through holes, and we can just make the length of the nose longer to meet this need. And this brings us nicely into the closed loop, um, the closed loop slide, where, as Pablo said, it's a one-step operation. The plant would send the information to the Clavis controller. The PLC would look at this information, tie it with the look at its parameters, set the lamps up accordingly, and then the power tool would become active. The operator would then fit the sensor to the unit in question or the application. The power tool would then be located on the adjustment nut, and it would drive forward until the target tension has been reached, and you would get the lights to indicate. Now, as Pavlos has previously mentioned, sometimes in production lines, the cabinet isn't always in the operator's view, so you can have a light stack that is put in a position where the operator can see either if the unit is pass or failed, or you can even have the function where it works as the process is running, and then it changes when the process has stopped. So the beauty of having a closed loop system is the fact that it's very fast, it's very repeatable, and of course the main thing these days with all manufacturers is the traceability of tying all the data and sending this out to either local PC or directly to the plant system. Data is the way that the world is going, and we are capable of providing all this data with this controller. So we'll show you the video next, and hopefully you can use the words and the descriptions that I've just give there and put it into this visual video, and you should understand me better. So hopefully that video allowed you to use put my words into a much better visual explanation. But as Pavlos said at the very beginning of the webinar, pulley alignment plays a key role in how a belt vibrates and the performance of that application. So we have a client who asked us to integrate prior to him setting the belt tensioning of his application. He wanted to make sure that his pulleys were aligned. And as I previously said, because we have the capability of an in-house machine facilities and all the benefits that gives us, we are able to control and construct a very simple mounting fixture that was able to fit on the pulley. The laser would beam across the top pulley, and we are looking to align the two edges, the very edges of the pulleys, so that when the belt is running, it's running true. And also when we come to set the belt tension, the belt isn't being manipulated by pulleys being out of line and the belt being twisted slightly. So this client, not only do they want us to do this, they embedded it with the closed loop system. So the whole pulley alignment, because they were doing the pulley alignment and the belt tensioning in the same station or the station before. We would control the whole process from start to finish under one process. So that's the pulley alignment gets done first, and then the belt tension on top, and at the end all the data is tied in. It's stored on a local PC, as well as then being pushed to their plant system, so they have full traceability of everything that they produce. So this pulley alignment, as I said, had a local PC next to it, and what they wanted to achieve was they wanted these two pulleys to be within 0.5 millimeter of each other, and the two vertical lines here is the acceptance of their pulley alignment. And once the pulleys were in line, the operator would look at the PC, say, yeah, I'm in target. You'd send that information up into the database. He would then secure the pulley so it couldn't move again during the operation of the belt tensioning side of things. And he, at the end result, was what the client wanted. In fact, the feedback from the laser alignment and the pulley alignment has been very good and very encouraging. So we can have the ability to assist with clients' needs of having pulleys aligned. So be it in this application, it's for the bigger generator applications and not so much the small EPAS units, because it's sometimes the pulleys and the belts are embedded in the unit itself, and you haven't got access to be able to mount tooling to it. But yeah, that's it really from start to finish. And I think now, Pavel, I think if you want to conclude, quick brief of what you said, and I'll do the same before we've got some questions.
Sorry about that. I
Yeah.
was muted. Right. And right. Just to conclude, we have talked about the start-to-end process. We've talked about alignment and tensioning of systems. Today's webinar is about BMS, FourierBMS, so I'm gonna focus on the tensioning. We have two main models. We have the BMS03 and the BMS01. BMS03 is a read-only cabinet that can take any of the sensor heads that we've talked about. And the BMS01 is the most advanced one, which has the PLC. It can log data. It can provide output the exact tension as opposed to the frequency that the BMS03 can do. But most importantly, it can do a closed loop. So that means that we can actually read and set the tension within the station in one go, in one operation. In terms of the sensor heads, don't be afraid that your design is difficult, because we have a variety of different designs for the sensor heads. Not only we have four main categories, but we have a lot of different designs for each of these categories. We can modify them. We can create brackets for you. We have full capability of designing and manufacturing stuff. So we can handle this. And on top of that, as we said, the second criteria is pulley alignment. We can handle this one as well with the pulley alignment system, because this actually is really important for the pulley to work well and not show any any indications of wear and tear while the belt is running. Would you like to add anything else, Mark, onto this one?
I think the only thing, thank you, Pavel. I think the only thing we need to add is, which I'm sure you said previously, is that this cabinet can be used with any belt application. Where there's a need and a requirement to measure belts and collect data, this cabinet gives you it all. Not only does the FourierBMS give them the data, but one of the reasons is being an engineering base and being on site myself is the LCD screen. That really does help engineers find the best spot of measuring belts when they come to setting their heads up on their production lines and making sure they're getting good signals. And if they're always having, if they are having a bit of difficulty, they can use the oscilloscope and even call us. We have our feedback on our after sales and support is always exceptional and something that we pride ourselves on. And yeah, whatever your needs and requirements are, we're more than capable of finding a solution for you.
Yeah, I think we can make this into a useful questions and answers session. So feel free to ask any questions if you have. Do this by raising your hand, as we showed before, by indicating on this app. Just to mention here that we forgot to tell that we are quite familiar with closed loop systems. Is that right, Mark?
Yeah. So the closed loop system. Thank you, Pavlos, for reminding me. The closed loop system that we showed the video of might appear to be new, but actually it's not. In the late 1990s, we had a closed loop system on the auxiliary belts for Ford engines. So Ford asked us to make a mounting jig that would fit onto the engine and control the tension via adjusting an idler bolt that would pull the belt into tension. And this was, we did it for them back in the 1990s. We're just using a new method of doing it with a different concept and over a different application, but it's something that we've already done and got full capabilities to do with any controller. It doesn't have to be a specific one. We can integrate with Bosch, Stanley, Atlas Copco. The control cabinet can handle all the variants, because we know that even Ford, who you think would be under one banner, each plant within Ford's have different power tool requirements. So the cabinet may need some internal wiring changes to accommodate the different power tools, but the concept and the way we drive the power tool remains the same.
Yeah. Right. Just to remind that there is a reaction button down below where you can actually do this as a thumbs up and speak. I've asked you all to unmute so that we can have a conversation. If you have any questions regarding the presentation, what I'm going to do now is I'm going to share, I'm going to switch the video to show you how the cabinet looks like in reality. So. Right. So as you can see here, this is the cabinet on the right-hand side, and this is the pulley that we want to adjust. We can run this, as we said, with commands from the local PC or from the plant itself with a PLC. This is, keep in mind that this is the BMS03, so we have a read-only module here that we can have readings coming out of the module. Should I go with the demonstration since we don't have any questions? Just to briefly demonstrate. I'm gonna share my screen. Please feel free to stop me if you have any questions. Right. So. Hopefully you can see the black screen with some readings on.
Yes, we can, Bob.
Right, okay. So we can actually control the cabinet remotely. We can control it by the buttons, but I would like to show you that we can control it remotely by sending some commands, and I'm gonna send the S command. We can see here that we get a response that says, gives us the frequency, the quality factor, and the state of the belt. So it's slack, okay, tight. So we have a slack belt here. That means that the belt is not in specifications. It doesn't have to do anything with the quality of the signal that we received. It has to do with the specifications that the plant gives about the belt. So we want it to be in higher frequency than 92. So that means more tension. Now, this is the quality factor, as we said. We have it also in the laptop as well. We receive it as an answer. This one is the frequency provided in hertz. And this was a single shot. We can have multiple continuous readings. We see here that we press the R button and we see that on the screen that we have a lot of readings coming through. And then we can terminate this. I'm gonna stop sharing my screen so that we can see in a full view the cabinet. So now I'm going to the manual operation. I can run this by pressing the run button. Here we have the FFT, as we discussed. We can see a significant peak at 92 Hertz or 91 Hertz. We have a certainty of 1% or 1 Hertz below 100 Hertz. And we can see a second peak here, but it's not significant enough. So that means that we have a high quality factor. And apart from the FFT, we can run it in run mode and have the vibrations plotted onto the screen here. So these are the two options of the screens. And then we can hold the screen here and save it into the USB as well. I think that's with the demonstration.
Yeah. Any questions, anybody?
It would be interesting to know what kind of applications you have. So what kind of designs you have, or generally speaking, if you have any project in mind that you would like to put this into action. Right. I'm gonna switch my video as well. I think everybody has our contact details, so you can reach us and ask us any questions that you might want. We typically answer within the same day. Almost definitely, we answer on the same day any mails that we receive.
Okay. Thank you very much, everybody. Appreciate your time, especially in the evening.
Yes.
Thank you, Peter.
Yeah. I have one question about selection of different models of SAS head. Because last week I went to ZF group, former TRW.
Yeah.
They have 3 models of SAS head, but I have checked their products. Their products are most similar, and now they have a problem with the SAS head ordered recently, last time. But when they use another SAS head, it perform better.
So are you trying to say that they've got 2 sensor heads that are the same, and one works well on one system and one doesn't on the other?
Yes. One SAS head is marrying edge, not how to say, not face.
Okay, so one's measuring the edge and one's measuring the face.
Yeah. That is better than the marrying face.
So so just so we don't so I fully understand you. You're saying the one that measures the edge is giving a better signal reading than the one on the face.
Yes. Yes. The sense head marrying edge is better than the marrying face, belt face. So I don't understand why.
Pavlos, do you want to give your thoughts on this?
Yeah, when we're talking about the face, is it the fine line that we see here?
Oh, that's the edge. That's the edge.
So that's the edge, and the other one is on the face of the belt, right?
So it's the flat face is the top part, like we're doing that center, and the edge is a thin line.
Right. So that's what we're referring to. So the better readings are coming from the edge. Is that correct?
Yes.
Right.
Yeah.
So there are multiple things coming in my mind right now, but one of them is that we have. Are there any readings on the belt? Is the belt what color is the belt? Is it a different color? Does it have different colors?
Well, what you can do is you can get a white edge.
They have two models, sense head or for sense head. One is for the marrying edge here. Another is for marrying face.
And the other one's for the face. Okay.
Peter, are they using the exact same head, or are they using two different types of head?
Yeah, two different types of head.
So they're both these. They look like these compact, or
yeah. This is like compact, but
right.
But the
different
satellite is on another side.
Yes.
Right. Okay.
Yeah. Okay.
One other thing is that is this an EPAS unit?
So my question is when we select sense head, what's the what should we select depend on?
Right.
Let me answer this. Peter, I think the thing with measuring the edge of the belt and versus the flat face of the belt is the fact that, as Pavlos first said in the beginning of the webinar, you can get other frequencies resonating across the width. And because that can happen, you've got to analyze what is really going on with the signal. So you might find that what would be interesting to ask your client is, when he is measuring with the edge of the belt, what kind of frequency is he getting? And what kind of quality factor does he get reported back? And then if he uses his other line, if he finds out the best signal that he can get using the time domain is actually switch to the Fourier, the FFT mode, and see what quality factor and the signal looks like then. Because one of the reasons why he's getting a more uniformed response from the edge of the belt is because you're only analyzing a very small section of the belt. You've got less influences sort of messing around with the signal that's being detected. Now that doesn't necessarily mean it's wrong, but also doesn't necessarily mean it's right, because if, as we've mentioned previously, if your pulleys aren't truly aligned, you might naturally have a higher tension right at that edge, but that might not be the true reflection of what it is on the flat face. because the flat face, if your pulleys are slightly aligned, which is not uncommon with EPAS units, is the tension. The tension. Sorry. Where were you, Pablo? Sorry. The tension here. Can you see my pointer, Pavlos?
Can you move it? Yeah, now we can.
Okay. Yeah. So the tension at this point, if the pulleys are splayed open slightly, will be greater, because in theory the span between the two is longer, and as the belt goes down the pulleys, it becomes that part of the belt has less tension in it, and it's the merging of the two frequencies, as Pavlos mentioned, trying to find the dominant one in the time domain might be giving your client the wrong interpretation of what's happening with the belt. So really, there's no real, the only real way to determine what sensor head is right for your application is to try on the same unit the two different methods. So in a perfect world, and I appreciate we're not in a perfect world, I would have one of your units in front of me. I would have the two heads connected to my system. I would put the frequency, let's say, at the target range of your client. So let's, for example, say 350 hertz. I'd put one head on. I would look at the signal, analyze it. So let's say we look at the edge, and it reads, say, 350. But then when I go to the flat face, I might read 320, and I would sweep the head across the width of the belt, looking at the signal, and then give that information to the client. And then it's the client's job is to say, okay, from the sample that we're looking at, we've got maybe 350 hertz at the front of the belt, but maybe it's 320 hertz at the back, because the pulleys aren't quite aligned, quite perpendicular. So remember, we're only measuring the belt and how it vibrates, and we can aid you with giving your client the right information. But really, it comes down to investigating what's happening with the belts versus measuring the edge and the flat face. In some cases, as you will be aware, you've got no choice but to measure the edge of the belt, because the belt flat face is buried inside the unit. But again, your client has to take into consideration all the key factors about whether the pulley is aligned, what if the tension of the belt is not quite uniform across the width. He has to make his own calculations and own assessments on the performance of the belt at that tension at that point.
Yeah.
Anything to add to that, Pab?
Yes. Bottom line, just to conclude what we said, is that bottom line is that when we are measuring on the face, we have a vast amount of points that we can measure. So that means that we can have different frequencies depending on the tension if the pulleys are not aligned. If they are not, if the pulleys are like that, that means that greater tension is at the edge, and shorter tension is at the bottom. And that might, if the LEDs are on a certain way, that means that it can get confused because it's getting a reading from across the width. But then when we're at the edge, which means that we can only take a specific line of points where the tension is constant, as we have a specific distance from one pulley to the other. It's not that the distance is going further apart or further closer. We have one distance, and hence we have one tension. But as Mark said, this is not necessarily correct or wrong. It is what it is. It is the reality. This is the tension that the EPAS is measuring. That's why further analysis is needed in these cases, where we can go to the FFT and look at what kind of frequencies exist. And that can provide us with details on what is going wrong. Maybe it's the position of the sensor head itself, and nothing else.
Yeah, and to add, Peter, I mean, what we do when we do some investigation work is we would, for example, we would mount something to this unit, so this sensor head could slide across the span and across the width. We may even changed the configuration of the hammer so that the hammer was hitting more towards the inside of the belt as towards the outside. So we would do a full in-depth investigation as to where we feel the best signal can be determined from. Which, as we know, sometimes it's very difficult to receive sample units from clients, but we're here to help, and please feel free to get your clients to talk to us directly. We'll certainly help them. But in this case, in the case that you've mentioned, it might be worth them just swapping the cabinet over from time domain to FFT and see what's happening with the signal then.
Right.
Yeah. I understand.
Good. Are there any more questions? I think
no more. No more for me.
Right.
No more.
I think we can leave it to that, Mark and Peter. And of course, feel free to get in touch and send us any mails if you have any further questions regarding the presentation and or the demonstration, or if you need any brochures of what kind of products we have. All right.
Okay.
Right.
Thank you, everybody.
Thanks, everybody.
Thank you. Thank you.
Have a nice day.
Bye-bye.
Bye.
Bye-bye.